Today, I'm going to show you how to make a lithophane. A lithophane, incidentally, is not new. You've probably seen them before. They have become repopularized, however, due to the advent of 3D printing technology. You create an image that with a backlight can be 3D printed and looks really cool. Let's see what an actual definition here. An etched or molded artwork in very thin translucent porcelain that can be seen clearly only when backlit with a light source. I want to show you the porcelain kind because those are pretty cool. And they're old, relatively old. Fancy, very fancy. I'm guessing these are molded, likely. There's a ton of other tutorials on this. If mine doesn't answer all your questions, or if you want to explore some other methods or techniques, but this one today is pretty quick and easy. This is actually the way I have done them in the past. So I got a couple pictures of Martin Luther King that I downloaded here. I'm going to try doing this with each one. I'm going to drag and drop the image. There's a couple different methodologies. There are a couple different websites. I believe you can use Blender quite easily, which is a free software that's very, very powerful. Here's a little instructable on how to make lithophanes in Blender. There's the old Mona Lisa. I have actually done the Mona Lisa in the past, but that's not how we're going to do it. We're going to do it with this awesome website, 3dp.rocks/lithophane. So, as you saw when I dropped that image, it automatically generated the file for us. So if I go to download, it downloads the three-dimensional geometry file here, the STL file. Stereolithography is what STL stands for. And here it is in all of its glory. Looking super fancy. The back. Incidentally, here in Mesh Mixer, which is the program we're using, click W and it shows us all of the individual shapes that represent this geometry. They're all actually triangles. But if I go here to select, this little circle here is my selection tool. Now I've selected triangles. I can actually manipulate these triangles here in Mesh Mixer if I want to, just to show you. Select those triangles and then I can do all kinds of stuff. But I'm going to hit cancel and I'm going to leave it, hit escape, and hit W for wireframe again. And then I'm going to go over here to let's use Prusa. Could also use Cura or Makerbot, which you would generally end up using in the library. Makerbot is probably the most commonly available printer for you guys. The downtown branch, we've also got some Lulzbots minis. Alright, so we've got our file, our resolution looks good, our infill looks good-ish. It depends. That infill can be seen. It's probably best if we do it at higher infill, I believe. Slice now. And it's going to create each individual layer. That's what it's doing. It's slicing. There's a couple limiting factors of the resolution of the printers. If we print it, when we look at this, this actually looks like it was printed flat on the printer bed. If we do it flat on the printer bed, kind of like this, our X and Y, let's see here, this green arrow is Y, the red is X. The X and the Y resolution is limited to the accuracy of the motors that control the machine. The Z resolution, which is the this blue arrow, the Z resolution is greater. I can actually get more precision. No, that's the layer heights. So I can get up to 50 microns or 0.05 millimeters in my layer heights. Whereas in the X and Y direction, my resolution is limited to my nozzle size, which is 0.4 millimeters. So if we use a smaller 3D printer nozzle, we can actually get greater resolution in the X and Y. The same kind of motors are used on the X and Y axes of these 3D printers. My Y motor right here, right there, excuse me, that's the X motor. The Y motor's underneath it in the back there. The Z motors are there and there on either side. They control these threaded rods, or these nicely machined precision ball screw rods or whatnot. This motor is like the same as that motor, the same as that motor. They're all the same accuracy. Now, the tightness of these machined threads or spirals on these rods do affect the accuracy or the precision. And if you look closely, if you can see them, the belt that controls the motion and the Y, or excuse me, the X and the Y is one underneath here. Those belts have a resolution associated with them. This one shows it pretty well. Basically the same design here. This belt, see all those little teeth? This belt's got little teeth on it. This is using, I believe, a cheaper threaded rod. Those teeth and cuts or whatever in the machine parts, those affect the resolution the same way as the accuracy of the motors or the precision of the motors. But either way, if you're using a 0.4 millimeter nozzle, this thing right here, your resolution in the horizontal direction is limited to whatever the size of the nozzle is. So here's a couple nozzle diagrams here. 0.25 millimeter nozzle, 0.4, you can see the opening's a little bit larger, 0.6 a little bit larger, 0.8 a whole lot larger. If you use a 0.8 millimeter nozzle, your resolution is limited to 0.8 millimeters in the X and Y. This will be a whole lot easier to see and explain to you if I print some things and show them to you. Here's a great example. So with the 0.15 millimeter nozzle, some really good detail. 0.6, a lot less detail. But this 0.6 millimeter nozzle printed part probably took a quarter of the time approximately. Is this if you're printing larger things? Anyhow, we're printing what we're printing with the 0.4 millimeter nozzle here today. And this is basically what it's going to print layer by layer. Starting with the first layer, second, third. Zoom in a little bit, you can see it. So, our layers are 0.15 millimeters, and that should make this work pretty darn well. I'll show you what it looks like when it prints. We'll probably do a couple other examples here. We could use this. Chose the file and create the STL. Either way though, you do a whole bunch of them. I'm telling you, you do the flat one, you do it flat like this, it's going to look kind of goofy like this. This looks okay, you can tell with this, but see all this splotchiness? That's from the nozzle making contact with the print. And it just doesn't look as good as if you do it vertically. So, say we want to do, this is a much better example. I'll show it to you here. Oh wait, I'm going to download the G-code. I'm going to export the G-code to my desktop. We're going to call it MLK1 vertical crucial PLA, and for 0.5 hours. Come over here, delete this. So, okay, this is what I was talking about. If we print it like this, it's gonna look weird. If we rotate it though, we print it like this, it's gonna look a whole lot better. It might struggle a little bit. Looks like we have some overhangage going on. Probably be okay. It's also going to struggle because this is straight across. It's a lot of vertical structure with a tiny little footprint. With that last file that was curved, I had a lot more strength. So if I were going to do another one, I would make a recommendation here. Say we pull this over to here. Go back to another outer curve. Well, I would just go ahead and make a recommendation. Do a curve, or at least a slight curve, just like this. This is probably going to turn out pretty darn well. I might struggle. I got some more overhangs. It's going to have a little bit of trouble printing that perfectly. It'll probably be okay though. Let's see the last one, see what it looks like. Definitely a lot of overhangs going on here. The lettering in particular. I believe the lettering is so pronounced because the lettering is totally saturated or white. So apparently the lighter colors are pronounced, whereas the dark ones are deeper. We can actually adjust the settings here if we wanted to. The thickness, thinnest, the amount of the curve. We can adjust all that stuff. And we can also adjust the images themselves if we know how to do that. And it can result in different detail specifics or model details. Anyhow, let's go ahead and mess with our first print. See how it goes.